I tried the same with the conference recently. We also wear like so many. Almost every day we have to wear like kind of the same colors. And everyone's like, "Are you wearing
All right, it's 10 o'clock. I think that means it's time. Welcome, everyone, to Lieke van Son's PhD colloquium. Welcome, colleagues, family, friends, anybody who might be watching online. Right, so Lieke came to us from the Netherlands, where she received her a bachelor's degree from Leiden University, and then her master's in cosmology. And then she came here about 4 years ago, planning to work with Selma de Mink, who's also here. Welcome back, Selma. And on the topic of her thesis of massive star binaries and their connection to gravitational waves. Now, as fate would have it, Selma would shortly after take a position at the directorship at Max Planck Center and continue to be the primary academic advisor for Lieke while she was here. But Lieke needed a local mentored advisor, and I was happy to fill that role. So for the past 2 years, I've been Lieke's mentor here. Now, this is not my field, and so in our weekly meetings, it was a real pleasure to basically learn from Lieke every week. I got to ask a lot of really stupid questions about stars and black holes, and she was very patient, and I learned a lot during that time, so it was a lot of fun. One of my favorite things about, maybe not the favorite, but one thing I really enjoy about being an advisor is telling a student when it's time to graduate. Something I think I'm pretty good at. And it, without fail, it doesn't matter if you have been here for 4 years or for 6 years, if you've written 2 papers or 22 papers. When I tell you it's time to graduate, you won't believe me. And you will beg to stay an extra year. And that was indeed what Lieke also did. But I'm happy to say she took the advice of me and also the committee, applied to many postdoctoral positions, including many prestigious ones, and I think received offers from nearly all of them. So that's how I get to embarrass Lieke a little bit. So she was very successful in the job market, and she decided to take not 1 but 2 positions and combine them into a 4-year position where she'll be at the Flatiron Institute at New York City, followed by a fellowship, Spitzer Fellowship at Princeton University. So I think I was right in the end. You were ready and certainly now are absolutely ready to move on to the next phase of your career, which will hopefully be very long and productive. But before we get there, we have some business to take care of. So we're going to hear from Lieke in a moment, the public part of her dissertation, and then we will adjourn for the private defense. Presuming that goes well, we will have a champagne toast after lunch sometime around 2 or 3 p.m. So be on the lookout in your inbox for that. And with that, let's welcome Lieke to her final presentation as a graduate student.
Thank you very much, Charlie, for that introduction. It's always important to note when you're right. So without further ado, I would like to thank you all for coming to my dissertation defense talk. And I'm going to be thanking all of my lovely collaborators and a lot of you here in the audience at the end, so as to prevent me from sobbing through this whole presentation. So I'm just going to start with the science and talk about the topic of my thesis, which is called The First Pieces of the Gravitational Wave Progenitor Population Puzzle. lots of words. Let me start at the beginning to tell you what I actually mean. So, at first, there was silence. But then, there were gravitational waves. The sound that you just heard is the sound of the first ever detection of two black holes spiraling in and merging together. And it was detected not with electromagnetic light, which we use to see each other, but with ripples in space-time called gravitational waves. Now, of course, this was a monumental discovery because it's something as if for the first time we can see UV light or X-rays, but then it's even bigger than that because we don't just see another wavelength, we see a whole new force of nature. And it's similar as to before we could only see the universe around us, and now we can also hear it. The first detection of a binary neutron star merger sounded something like this. And it was equally, if not more, exciting because it showed us how we can also combine electromagnetic observations with gravitational wave observations to form a full picture of our universe and study these exotic objects like black holes and neutron stars. By now, we have about 90 detections of not just merging binary black holes, but binary neutron stars and also black hole neutron stars. And this means that we are now at this extremely exciting tipping point in gravitational wave astronomy, where we're moving from the initial excitement and phase of discovery to a phase of bigger data and population synthesis or population studies, because we can now infer properties of not just one single black hole, but the whole population as a whole. And I think that contains so much more rich information. And even this is really just the beginning of an era of gravitational wave astronomy. Because this plot shows the number of detected events in log scale on the y-axis as a function of the time. And you see that the thesis that I spent here about 4 years, it began with only of order 10 detections, but by now we have of order 100 detections. And next month, when commencement happens, hopefully, kind of, then also hopefully the next observational run, 04, will start, and it will probably give us about 2 to 3 times the events that we have today. And in the next 5 to 10 years, we will almost increase the size of the catalog by 30-fold. But in the following decade, we're going to move with next generation detectors to hundreds of millions of detections of these double compact object mergers. And so the prospect of all these detections raise some very big questions. First of all, how did they form? Where do all these merging double compact objects come from? And secondly, which is a question that's very close to my heart, what can they teach us about their direct ancestors, namely massive stars? So these questions are the broad questions that govern my PhD and my work in more general. So let's dig a little deeper into what I mean by them. Firstly, how did they form? So gravity is actually kind of a weak force. And to get two black holes to in-spiral within the age of the universe, you have to place them on a very short orbit. Such a short orbit that we think that their progenitor stars, which were at some point much bigger, would never fit within this space. And so we don't know how to get two black holes, or the question is how to get two black holes so much closer than their progenitor stars could have been, because these progenitor stars would have just merged and formed a stellar merger, not a black hole merger. Now, this challenge is often referred to as the separation challenge. And there have been many different formation channels proposed to solve this problem. Generally, we can divide these channels between two camps. The first are isolated binary evolution channels, where we start out with a binary that is already born as a binary star pair, and they lose angular momentum and shrink the orbit through binary interactions like mass transfer or tides. The second are dynamical formation channels, where we assume that the black holes or compact objects are being brought close together through dynamical interactions in dense stellar environments. All of these channels The physics behind all of these channels also means that there's a lot we can learn from gravitational waves, ranging from how the gaseous disks around active galaxy nuclei work to how binary evolution works. And this is why figuring out what the dominant formation channel is such a hot topic in gravitational wave astronomy. But specifically to learn about these massive stars, this brings us to my second question. What, if anything, can they teach us about our massive stars? Because all of those formation channels depend still crucially on the direct ancestors of compact objects, namely massive stars. These stars, when I refer to massive stars, I mean stars that are about 10-ish times more massive than our own sun. And they are when they die, they will form either black holes or neutron stars. So massive stars are extremely important to almost all different fields of astronomy, as they shape our universe through the radiation that they emit. They dominate the radiation of the early galaxies that we observe with JWST, and they shape the chemical evolution of our universe through the elements that they produce, like oxygen. Unfortunately, massive stars are also very hard to catch while they're alive, because they live fast and die young. This means and they're also intrinsically very rare, so it's hard to observe them. Furthermore, they also include an enormous scale of both temporal and spatial physics, making it also very difficult to model them from first principles. So the challenge really is, and not to forget, massive stars actually live in binaries, which is really cool because that gives us all kinds of binary interactions, but also lots of extra complications, basically double the trouble. So the challenge really is these massive binary stars. And because of this, because they're so hard to catch and model, there's many different uncertainties involved in modeling their evolution, like their wind mass loss or their supernova kicks, or basically too much to put on one slide. So what we need to make sense of these gravitational wave observations is a tool to efficiently explore all these different uncertainties and see how this will affect our predictions for the population of double compact object mergers. Now, this is precisely the goal of rapid population synthesis. So rapid population synthesis simulations basically take approximations for single stellar evolution. They combine it with approximations for binary evolution, and they use that to combine a model for binary stars that allows us to model a binary evolution in less than 1 second. And so we can probe the many different formation pathways and outcomes of these massive stars quickly, so that we can focus on those pathways that lead to what we are interested in, namely gravitational wave sources. In my work, I typically use the code COMPASS, which is a beautiful code that is completely publicly available and very well documented, but I'm also very biased because I'm part of the team. But there's definitely many different codes out there, but they all are based on somewhat of the same underlying mechanism. Now, I would argue that population synthesis is a necessary tool to make sense of these gravitational wave detections, but they come with a big asterisk, and that is, in order to be rapid, they all rely heavily on crude assumptions about the underlying physics that's in there. And so in the word of George Box, all models or population synthesis simulations are wrong, but at least some are useful. And in particular, I would argue that population synthesis can be a very useful tool to uncover universal truths, so those things that are true regardless of all the uncertainties that we have to deal with, and to use them as a controlled experiment to show if we just vary this one parameter, how will this affect our predictions? So it can be used as a playground, really. Now, okay, with this tool in hand, I want to move to what the title of my thesis is, and move to these first pieces of the progenitor population puzzle. Basically, I want to figure out What are the progenitors of these gravitational wave sources? And what have we learned so far already from the sources from the detections that we have made? So let's turn to some observations. What have we learned so far? Well, lots of things, but my favorite lesson is really that there are features in the mass distribution of merging binary black holes. So this plot, you will see it a lot, and it's the primary black hole mass, so the more massive black hole component as a function of the rate. So that just means more common and less common, and more massive and less massive. And as you see, it's not a straight line. So that means there are features. In particular, there is a clear feature at the low mass and at the high mass end. And I'm focusing a lot on black holes just because that's where we have the most detections right now. I focus on masses because the masses are by far the best constrained property that we can measure from gravitational waves. So this is also why they show features. Regardless of that this is the best that we have, the real picture is still a little bit more complicated. But for the rest of this talk, I will just stick to the streamlined version and to not complicate things too much and focus on the two main features. Now, why is the location of the features so interesting? Well, I just told you that there's all these different uncertainties that we have to deal with. One of the uncertainties is the metallicity-specific cosmic star formation history. That's a mouthful, but I'll tell you what that is. Basically, we don't really know when stars were born. So on the x-axis here, I have the age of the universe where left is today, and the Big Bang happens here. And apart from when they were born, we don't really know with what composition or with what metallicity they were born. And that matters a lot because the metallicity of a star determines how big the star will be and how strong its winds will be. And so it has an enormous impact on the life of this star and also its ability to form black holes. So the problem is that we don't really know what this function looks like, but we do know that, the universe started out some kind of forming stars pretty metal poor and ended up forming stars pretty metal rich today. Now, in order to capture this uncertainty and see what its effect would be on the population of black holes, we made a simple kind of flexible analytical model that depends on only a few parameters that are intuitive so that we could tweak these parameters between what we think is reasonable and test how it affects our predictions. And so this cosmic evolution, or the effect of this cosmic star formation history, is going to be the first piece of our puzzle. So we did exactly that. We took that cosmological model, we combined it with some assumptions for binary physics, and smashed together, you get this colored line as a prediction for the mass distribution of black holes. In gray in the background are again the observations. Now, the fun thing is that we can now also vary this cosmic star formation history. And so this single color is showing, I had a pointer thing, yes. So this is the parameter that we're varying here. And we're varying between the two extremes that we think are reasonable. And this shows you that we found that even though the rates change by a lot, the locations of the different features in the mass distribution actually don't change. So I'm going to flip over different variations where we are varying different parameters. And you will see, I'm focusing on the low mass end because that's the clearest one, but you will see, although everything goes back up and down, the location of kinks and bumps stay at the same mass. This is really exciting because it means that there's a hope for us that the location of these features actually tells something about the underlying binary physics rather than just showing us this uncertainty in the cosmic star formation history. So let's go back to this distribution and focus on one of the features. And I want to start with the high mass feature. This feature received a lot of attention, basically because people thought, and it's going to be my second piece, and basically it's because people thought that we could not form any of these high mass black holes due to something called pair instability supernova. So pair instability supernova are basically, it's basically as follows. If you were to plot the mass of a star and the remnant mass of the black hole that it will form, you will initially expect that a more massive star will give you a more massive black hole. And this is just through normal core collapse supernova. However, if you reach a certain stellar mass, the stars will form pairs of electrons and positrons in their core, causing a premature collapse that explodes the star too early, leaving no remnant behind. And so this sets a maximum mass for the black holes that we think can form from these stars. If you go to even higher masses, the stars will encounter photodisintegration in their core, and so that prevents the explosion from happening, and you can form black holes again of even higher masses. And this is why we call this the parent stability supernova mass gap. Yet, we've seen black holes that merge with these masses. And this was so exciting that it even got picked up by news articles outside of astronomy, where this New York Times article summarizes it pretty well. These black holes shouldn't exist, but there they are. Now, this is exactly the kind of questions that you have to give to theorists, because if you tell them, you know, this thing should not exist, but it's there, they're going to be finding 1 million, everyone and their mother will find like 1 million ways around it. And that's exactly what happened. So there was a storm load of papers of how do we form these very massive black holes. And what we did was actually set out to test one of these different models and see if it would actually give us black hole mergers in the gap. Specifically, we looked at accretion onto the black holes post-black hole formation. Because these black holes, I just told you that they can't form from a star directly. But what if they just accrete from a companion star and then form a black hole with a mass in the gap? And this is actually pretty common. So what you see here is a star that's transferring mass, or an artist impression of a star that's transferring mass onto a black hole, which happens very often. We see this happen very often. But we normally think that these black holes don't accrete much mass because everyone traditionally assumes that the black hole accretion is limited by the Eddington rate. And the Eddington rate is very low, as you might remember from your stars class. And so it basically means that these black holes don't really accrete anything. But we thought, okay, what if we set out and say that you can just forget about the Eddington rate for a little bit and let the black hole accrete whatever it wants? So what you get, this is now the total black hole mass, and this is a fiducial model that is Eddington limited. If you let these black holes accrete very much above Eddington, you indeed get systems that form well within the gap. But these black holes won't actually merge. Because when you transfer mass from a more massive accretor to a less massive donor, then the way that the angular momentum is, specific angular momentum is lost from the system dictates that the binary orbit will widen. And so wider systems will take too long to merge, and you don't actually pollute the gap at all. So our conclusion was really, this is not a valuable or not a valid way to pollute the black hole mass gap. There's many other channels or exotic channels out there, but I'm not going to discuss them today. Instead, I want to discuss another way of, okay, but then how did these massive black holes form? And the other way is, what if we were just wrong about the location of the parent stability mass gap? Now, initially, this was thought to not really be the case, because this location of this gap was surprisingly robust against most uncertainties that we have in massive stars. However, there is one thing that it's not robust against, or what it still depends strongly on, and that's the carbon-oxygen alpha rate in the core. And so in 2019 and 2020, Rob Farmer wrote a beautiful paper showing that the gap should start at about 45 solar masses, which is already a little bit too high from the observations. But a more recent paper from Farag et al. Shows that the gap is actually supposed to start at about 60 solar masses. And so you can implement these new results into population synthesis to look at what this would look like, and if it would still be able to explain the gap that we see, or the bump feature that we see. And that's exactly what David Hendricks did here. And so each of these colors is a model that represents a variation or is representative of a variation in these carbon-oxygen core masses, reaction rates. And the old fiducial is highlighted here in blue, which as you can see was already kind of off of this feature. But the new rates push the gap all the way up to about 60 solar masses. So the takeaway from this figure is just it doesn't really match. And to go back and take a moment to give an overview, we've seen that the uncertainties in the cosmic star formation history do not affect the location of features, giving us hope that we can learn some physics from them. And secondly, we've seen that mergers with masses above this high mass feature could either be explained by exotic formation channels or by the nuclear reaction rate just being different than we initially expected. Now, my money is definitely on the nuclear reaction rates if anyone wants to place a bet. But let's move on for now. So, okay, that's all for the high mass feature, but there was also this low mass feature that we've seen, and that's also more solidly detected. This feature has received significantly less attention than the high mass feature, and I think that's a waste, because I think it's actually more interesting for two reasons. It's got to be third piece. The first reason is going back to this uncertainty in the cosmic star formation history. So when we did this experiment, we also saw a second, could draw a second conclusion, and namely that is that the variation of the rate at low masses is always lower than the variation of the rate at high masses. So what I'm showing here is the same variations, but I'm highlighting how much the variation between the least and highest rate prediction is. And you can see that at the high mass end, it's often a factor 10 to maybe even a factor 100, while at the low mass end, it only varies over a factor of a few. So this is cool because it means that we have even less uncertainties to worry, or we still have a lot of uncertainties to worry about, but not that much this one. Secondly, normally we're all very confused about what formation channel we're actually looking at. We don't really know which formation channel is causing the black holes that we see. But at these low masses, there's only two channels that are expected to be able to give the global peak of the mass distribution at about 9 solar masses. These two channels are the main channels of isolated binary evolution. Basically, if you have a binary that evolves through different phases towards a merging binary black hole, it will encounter mass transfer on its way. And this mass transfer is determining what kind of outcome you will get. If you get unstable mass transfer, it will lead to a common envelope, and we will call it the common envelope channel. However, if you only go through stable mass transfer, then we call it the stable mass transfer channel. It's pretty simple. So let me focus a little bit more on what I actually mean with this low mass feature and zoom in. So what we've detected, or what LIGO and Virgo seems to have detected, is that there is a global peak or the feature happening at about 9 solar masses. Now you might think, okay, 9 solar masses, why not? But you're wrong, because you should be surprised, given the initial mass function of black holes, or of stars, dictates that the most likely progenitors of 3 solar mass black holes are about an order of magnitude more common than the most likely progenitors of 9 solar mass black holes. So I would argue that in order to understand why this peak is at 9 solar masses, we really have to ask ourselves, where are these low mass black holes? And so this question might sound pretty familiar to a lot of people, but I still want to be very agnostic. In my opinion, there's only just 3 options. The first option is these black holes exist and merge, but we just don't see them. We miss them because there's an observationally bias against detecting low mass black holes. Now we actually know that we are biased against low-mass black holes, but we also know how much we are biased. And regardless of that, we still think there seems to be a dearth. Moreover, the next crop of observational data that is coming very soon will most likely just give us the answer here. It will show us if there really is nothing in that low-mass end, or if we were just fooled by an observational bias. The second option is that these black holes just don't exist in nature. This is what's known as the neutron star black hole mass gap, and it was first proposed based off of X-ray binary observations of more than 20 years ago. When these X-ray binaries were observed, they also saw a lack of low-mass black holes, and they proposed a theory that said that maybe the supernova for neutron stars and for the lowest mass black holes are just kind of different, and there's a gap in the remnant mass function between the most massive neutron star and the least massive black hole that you can form. However, as soon as this was proposed, it has also been debated very much, and there have actually been multiple claims against finding black holes with masses in this mass gap. A lot of these claims, to be fair, have also been knocked out of the park by Kareem, but there's definitely still an open debate on whether or not there really is a gap at this low mass end. And that brings us to the third option. What if these black holes can exist in nature, but they just don't form gravitational wave sources? Now, this is what I would call an evolutionary selection effect against forming these merging double compact objects. And would we expect an evolutionary selection effect? Well, the answer is overwhelmingly yes, because gravitational waves are just a very small subset of all of the massive stars that are out there. So they are inherently a very biased population. But moreover, what we did in this work is show that specifically for the stable mass transfer channel, which remember is one of the only two channels that is relevant in this mass regime, we found that the stable mass transfer channel will not form low-mass binary black hole mergers, regardless of what you assume for the supernova mass function. And this was quite a surprising find, because the underlying reason for this is the stability of mass transfer itself. And so this shows here that if you make different assumptions for what the stability of mass transfer is, a gap between the most massive neutron star and least massive black hole will open up or close. So which of these three options is it? Well, I have very high hopes that we're going to know this for certain very soon. As I told you already, the first option we likely know from gravitational wave detections within the next 5 years or so. The third option, if it's an evolutionary effect, then we will only keep seeing this in the gravitational wave observations. So we will see a dearth of low-mass black holes in gravitational waves, but not in black holes detected through other observations, like electromagnetic observations of black holes. And so if also in other observations of black holes, like electromagnetic observations and radio velocity, etc., there's no black holes with these masses detected, then it's more likely that it's the middle options, that they just don't exist at all. And luckily, I also have very high hopes for the different electromagnetic observational surveys that are coming out, that are already there and coming out, because as you can see, it is a very biased overview of different observational surveys that there are as a function of the electromagnetic frequency and all the different kinds of cool physics that we can do with it that will help us constrain our models of massive stars. And specifically for this question of, is there a neutron star black hole mass gap, we will have to see if we can detect black holes through radial velocity measurements. Even microlensing has been achieved now, or using Gaia photometry. And I think that is ramping up now, so we'll definitely, or hopefully, have an answer very soon. And that is very cool, because remember that this question of a neutron star black hole mass gap has been debated over for more than 20 years. So the prospect that it would be solved soon is, I think, kind of impressive. Okay, I want to move over to my last piece of the puzzle. I added there. And tell you that so far, I've only been talking about the low redshift distribution. So I've only been talking about the mass distribution at redshift 0. But there have already been indications that the black hole merger rate is not constant with redshift. So if you plot the rate of black hole mergers as a function of time, you see that it used to be higher before. And so the way that the rate evolves with redshift shows us or contains a lot of information about how massive stars lived in the very, very early universe. And that is shown by this cartoon. So this big gray blob is our universe, with the Big Bang over there and us living today. And even though that the current gravitational wave detectors only reach the local universe, massive stars that were born in the very early universe lived and died pretty fast to form from binary black holes in less than a couple million years. But it can take them several giga-years, anywhere between a few million years to several giga-years, to spiral in and form a gravitational wave event. And so that means that even though if we detect a merger today, it can be coming from something at the very high redshift universe. The key to understand and to link this detection to that early universe is the delay time, which is what we call the time of the star's life and the in-spiral time. Unfortunately, we cannot detect delay times directly. What we detect is only just the masses and spins and mass ratios of these merging double compact objects. So linking this delay time to observable properties is a key way to unlock this high redshift universe with gravitational waves. So this is exactly what we did in this work, where we asked the questions, are delay times correlated to any observables? And what we did was, again, look at our usual suspects, namely the common envelope channel and the stable mass transfer channel. And we're plotting here the mass as a function of delay time. And what we'll see is that these different channels actually occupy a very different regime of this plot. Specifically, the common envelope channel barely forms black holes with masses above about 25 solar masses. And this is a result that has since been reproduced by multiple different codes by independent groups. And secondly, we see that the stable mass transfer channel doesn't really form short delay time systems, though it can form these high masses. So the second important question is, would we be able to observe this effect then? So what we're doing here is making a prediction for what the black hole merger rate with redshift is. And remember that the common envelope channel will have shorter delay times, lower mass black holes. The stable mass transfer channel has longer delay times, but can form these high mass black holes. And so what we see here is that indeed the low mass black holes with these short delay times will follow the cosmic star formation history, here indicated with the dashed line, whereas these high mass black holes will have longer delay times and a much flatter evolution. And so this different slope is a solid prediction that we can measure in our data. Unfortunately, so far we've found insufficient evidence for the evolution of the rate with redshift, but we are really just at the beginning of these observations, because we've only just started probing the rate redshift evolution. And that is very beautifully shown by this plot. Here on the y-axis is the horizon redshift out to which we can detect certain systems of a particular total source frame mass. And this blue curve shows our current detectors, which are already able to detect out to about redshift 1. But next generation detectors are just going to be blowing us away with measurements of redshifts of about 100. And note that how specifically the regime where we expect stellar mass binary black holes to live will have basically a complete set of our sample. So any question of, is there any evolution with redshift, will just be solved. Now, I want to take a moment and show you how incredible, how crazy redshift 100 is. Because if you were to take the universe and cram its history into 1 year, with the Big Bang January 1st and us living all the way in New Year again, then redshift 100 is 60 million years after the Big Bang, which means it's 10 a.m. on January 1st. Whereas we only expect the first stars to be formed on January 3rd. So that's quite crazy, right? How are you going to form these black holes if you didn't even form stars? Well, that's why we can be so excited about signals of maybe primordial black holes that are not of stellar origin, or even, but even if we don't see primordial black holes, because we don't even know if they exist, we will for sure know that there's evidence of population 3 stars that we're seeing. And because we're measuring almost all of this calendar year completely, we'll have a measurement of the cosmic star formation history from gravitational waves that is independent of electromagnetic observations. So lots of cool things. And just for reference, by the way, the solar system only comes around somewhere in August in this picture, much later. And again, we are only just probing the tip of the gravitational wave iceberg. So this is a similar image as I made for the electromagnetic spectrum, where we have, just as for electromagnetic light, we have also different frequencies of gravitational waves. And at the moment, we're only seeing the gravitational waves that we can detect on Earth. But we're opening up this gravitational wave spectrum, and with it, we will see many different sources that we, at the moment, just cannot see, ranging from massive or supermassive black hole in spirals to galactic double white dwarfs. So I think it's just an extremely exciting time to be working on gravitational waves, especially because there's also going to be a lot of unknown unknowns. So, to summarize, I hope that I've convinced you that behind each of these small pieces of the gravitational wave progenitor puzzle, there is a lot of science hidden. And there's already so many different questions and physical information that we can get. But of course, this is really just a small piece of the big puzzle that still lies before us. And I personally am very excited to keep on puzzling in the next couple of years and to continue to form a picture of their massive stellar ancestors. So with that, I have to move to my acknowledgements. And as Charlie already alluded to, this PhD was actually quite a journey. It started with Selma in Amsterdam. And Selma, I just want to start and say thank you for seeing my potential and always going above and beyond to help me realize it. So this is me being very excited to start working on gravitational waves. But very soon, and like only a couple months after we started here, we already knew we were moving to the CFA. Even those couple of months, though, were enough for the UvA and Amsterdam to be super supportive, to be like, Amsterdam will still support you, which is why I still have collaborators there. But moving now to the US, I got to meet my thesis advising committee here. So Lars, Ramesh, Josh, Charlie, I want to thank you all for giving me lots of advice over the years. And Charlie in particular, I want to thank you for accepting me into your group. I think it's been lovely meeting with you every week. And I hope you now enjoy binaries a little bit more. Because I remember you distinctly saying a couple weeks ago during group meeting, oh, I can't believe that we're having all these conversations about binaries now, as if that's a shame. So I hope you continue to talk about them when I'm not there. But after not so long after that, if you might all remember that Corona happened. And so everything moved online. And Selma, as Charlie mentioned, moved to a director position at the MPA. But as everything was online already, she just said, no worries, I'll keep on advising you remotely. And indeed, Charlie said, no worries, you can just join my group. So multiple advisors. At the same time, during all this time, I've also always been interacting a lot with the lovely people of the Compass group, who I all would like to thank as well for being just awesome collaborators, and especially Ilya for being a great remote mentor. And I've seen Ilya so much that last December, when I actually met him for the first time in person in Australia, he did not believe me when I told him this was the first time we met in person. He was like, no, we've met. I'm pretty sure I would have noticed if I had traveled to Australia. So at this point in my PhD, I thought, you know what? I don't have enough affiliations. So what I'm going to do is I'm going to go to New York for a couple of months to work with the Gravitational Wave group there. And that's also people that I would really like to thank them for hosting me, especially Will Farr and the Gravitational Wave group. You people are all amazing. I love all the science that we've been doing. And apart from these more senior, I would also like to thank Stephen, who's been along with all of this journey and who always gives me much more useful advice than he seems to think himself. And I would also like to thank my PhD brothers and sisters, Eva, Mathieu, and Ilva. You've been both friends and mentors to me. And of course, so many other people that I want to thank of all these different collaborations, but that I just don't have the time or all the photos to find. But I want to particularly take a moment to also thank Lisa and Peg here for supporting all of the students, including me, through all of the difficult things that you have to encounter as a PhD. You really need to get some photos of yourself online because I can't even find. I tried very hard. And I think if I've learned one thing of this whole PhD endeavor around the world, it is definitely that there is a lot of fun and cool people out there. So I'm just really excited and thankful that I was able to go through all these collaborations around the world and have all these well-known, infamous Lars's wine meetings. Which have also been a highlight of my PhD. To all my fellow graduate students, thank you so much for making the CFA into this much more sociable and much more fun place that it has ever been before. In particular, thanks for Floor for always, apart from being a good friend, sticking out and somehow finding the time to make everything around you a better place. I also want to thank Nymeria, who, from her eyes, it's a bit dark, but you can understand. She understands how difficult a PhD can be. She always kept me focused and judged my work when I wasn't really sure. And I guess I also want to thank her owner, Gus, who, apart from roommates, is also my office mate and a friend, and also driving instructor, by the way. Taught me how to drive in the US. Now, to all my many friends from home who I have so often missed during my PhD abroad, I hope you're all watching, and it's very fun. I'm very happy that you always keep reminding me that there is more in life than just astronomy. Now to Tom. I know you don't like the serious stuff, so you don't get a serious picture. But without your love and encouragement, I would have never made it through. And I can't wait for our next adventure together. And lastly, to my parents and my family, my grandma who might be watching online, and my parents and sister who are sitting here. And Dana, you're my favorite sister, and I'm so happy. I can't even tell how much you mean to me. And to my parents, your encouragement, and you've always been an inspiration for me. You're the reason I got into science and that I was able to achieve my ambitions. So I guess thank you all.
We have time for some questions. Anyone have questions? Timo.
So you were talking about there's a gap between the stars that could form neutron stars and the stars that could form black holes.
Yes.
What happens to the stars that form neither? Is it just that?
Yeah, so the idea is that, or some of the theories are that if you form a neutron star, you will get a successful supernova explosion, for example. And so you'll just blow away all the outer layers. But if you get to a more and more massive star, at some point, maybe this supernova will be unsuccessful and the mass on top of, on the higher layers will fall back. And so because there's this kind of layer laying on top that you either do or do not expel, you will get a jump in the remnant mass distribution. So if you do expel it, you get a neutron star. If you don't expel it, you get a black hole, but not with just one solar mass more, but like with 3 or 4 solar masses more. If that makes sense.
So it still explodes, it explodes entirely.
Yeah, you use it's fallback, basically, is what we call it. If some of the mass falls back, then you can form a black hole that's more massive.
Oh, I see. So, okay. It just like collects more mass
Yes.
at the last minute.
Exactly. Yeah, and the details of this go really into the details of the convection-driven explosion of the supernova, like how fast that happens and how much you can expel or how much will fall back.
I see. Okay. That makes sense.
Yeah.
Something like that.
Nice talk, Lieke. I learned a lot. So I also have a question about similar, the gap.
Yeah.
So your paper explanation was that these binaries form, but they don't merge in the whole time, right?
Yes.
So I'm wondering if they would still, have you thought about that they might still emit gravitational waves, but at a lower frequency, and we might see this in ESA?
Yeah, so actually what we found is that these systems that would otherwise form these low mass black holes would go into unstable mass transfer, a common envelope, and merge instead. So they wouldn't form like white binaries, but rather they would form merged stars. But this is very uncertain because as soon as you get to like the common envelope part, then we don't really know that much. Well, we do. Sorry, Morgan.
That's accurate.
But yeah, so basically the theory here was like, if we focus only on the stable mass transfer channel, then the systems that would end up in the gap get lost because they form common envelopes.
Wonderful talk, Lieke. So you mentioned, I guess, in that cosmic chart that's like with the detectors, you could go up to 10 a.m. January 1st.
Yes.
I was curious, is there a theoretical limit to how early you could go before, I guess, like how much can like the observations push?
That's a good question. So, okay, first I want to put a caveat here and say that when we talk about the horizon, we really talk about the furthest part that we would maybe possibly see something. And realistically, I don't think we'll see anything like very certainly at that point, which Salva knows a lot more about as well. But interestingly, like at least gravitational waves will not be bothered by something like the Big Bang cosmic microwave background, right? Because we might be able to see beyond that. That's just the first moment that light started scattering, but that's not per se the same for gravitational waves. I don't know, there must be a limit though, out to which you can probably not see them anymore, but yeah. Morning.
Like
Money. Okay, money is the limit. If you find a billionaire.
I like how your first reaction, Tanvir, was predicted of 100. Why can't we go
This low redshift universe.
It looked like most of the models were over-predicting the number of mergers around 20.
Yeah.
Do we take that seriously? And if so,
That's a good question. I get this question a lot, and if I ever have time, I will look into it into more detail. But you're referring to this, so actually, this bump is seen in more population synthesis models. This is a model from binary C. I also see it in models from using COMPASS. And I know that some other people like Michele Mappelli have also seen it in their population synthesis. That doesn't mean that it's real. That just means that it might be wrong in all of these codes. But I have found that I can get rid of this bump by changing the mass transfer efficiency. So if you have stars interacting for the first time, then how much mass is accreted by the companion star is the mass transfer efficiency. And if you set that to 0, then you actually can get rid of this bump, because so these are things that switched mass ratio. That said, I still don't fully understand why they would form, and as long as I don't fully understand, I don't believe it. So yes, it's a hard feature to get rid of, but should we really focusing all our attention on it? Maybe not just yet.
So, very nice talk. But you didn't mention what I think is one of the biggest questions out there in this whole game, and that is, how do we form stellar mass black holes with K-dwarf companions?
Yes.
All the LMXPs, we do not have any sensible way of creating them. They certainly are not due to the evolution of two massive stars. K-dwarf rules that out. And that's also where the peak in the mass distribution of stellar mass black holes is best known, because those have been measured rather well. They could be improved, of course. Some of them are marginal.
Yeah.
But that's really the big picture.
That is, yeah, I agree. That's a really big question, and I also agree that I have no idea of how to form these systems. I think, yeah, you need crazy ideas, because normally, like you definitely were not going to do it with normal stable mass transfer ever, and like maybe some wild common envelopes and accretion things can happen. But no, I agree. There's definitely a lot more questions out there than I have discussed, and this might be one of the point where we should really connect all these dots, including this as well.
Sample, with the exception of one very recent one, the best evidence for the mass gap showing up. I mean, there's 0.4, well, I never remember these telephone numbers, but that is well measured to have a roughly 4 solar mass black hole.
Yeah.
And recently, there's this controversial, to some extent, but I think it looks pretty convincing, measurement of all the crazy systems, SS433, with a 4 solar mass black hole being dumped on by a supergiant, and so very high accretion rates, and that's what's launching that incredible jet that we don't.
The SS433
so
jet.
That's another.
Yeah, it's more. There's more to do. No, I agree. That is.
Let's take one last question from Kara.
Thank you. So I guess the other thing that you know well is the ratio between the two merging black holes. I was just wondering how that plays in as a constraint for your sort of theoretical model.
Surprisingly, you actually don't know the mass ratio very well.
No.
Mass ratios actually have a much weaker imprint on the gravitational wave signal that you see, and what you measure from gravitational waves is the chirp mass. And so the chirp mass is this combined kind of weird thing of M1 and M2, and it fits multiple mass ratios. So at the moment with the observations, we're not much further than just having this kind of power law fits to the mass ratio distribution. Although I think that we can do better, and I know there's some people working on trying to infer something more out of the mass ratio distribution, but it is definitely much harder, especially also because there's a degeneracy between spins and mass ratios that give the same effect on the gravitational wave signal, and so it's hard to know which one you're seeing. So this is why really the masses are the only thing where I can kind of trust some things.
I've been tricked by those beautiful cartoons just showing the...
Yes, yeah. We can predict a lot of stuff, but the observations are just not there yet.
Great. Okay, let's thank Lieke again.